The most important definition of acids and bases for AP chemistry is the Bronsted-Lowry definition. It's very similar in a lot of applications to the Arrhenius definition, but it looks at it from more of a reaction process as opposed to just individual atoms doing one thing or another. So a Bronsted-Lowry acid is something that can donate or give away its hydrogen, and the base is the thing that takes that in. So for the Bronsted-Lowry definition, they have to come together. We have to have something donating in order to have an acceptor and an accepting to have a donor. So right here, hydrochloric acid and ammonia are common acids and bases. And what happens there is that the HCl gives its H to the NH3, turning into NH4 plus and Cl minus. Or those same acids and bases, HCl and NH3, can react with other things and donate and or accept hydrogens from them. We could also see how the hydroxide ion acts as a base, or really almost anything that we define as an acid or base fits this Bronsted-Lowry definition. When you're looking at your acids and bases, you can either just know or look at the formula to predict whether something's an acid. A lot of times it starts with hydrogen. Many bases either end in hydroxide, or a lot of times they have nitrogen in them. They would be called nitrogenous bases, or they are derivatives of ammonia. But really, we do this a lot more by looking at the reaction from reactant to product side, what has fewer H plus ions and what has more H plus ions. And we'll see this in reactions over and over throughout these examples. But one thing that hopefully you can see in these examples right here is that water is involved. That doesn't mean that water all of a sudden raises and lowers its pH. It just means that in these instances, when it's with something more acidic, it can accept a proton. When it's with something more basic, it can donate its proton. And we see the result there. In those examples, water is doing something called acting amphoteric. So the same prefix there as amphibian, going in water or on land, it is doing both things. Water is a great example of things that are amphoteric, and we'll see a lot of other things. When you have more than one hydrogen in your formula, that means it may be possible to be amphoteric. As I look at these reactions here, and this is that first one from up at the top, we see that it's written at an equilibrium, meaning that my reactants can turn into products, my products can turn back into reactants. And when we think about it going backwards, we are still exchanging a hydrogen ion. From left to right, the hydrogen gives away, or excuse me, the hydrochloric acid gives away its hydrogen. But when I go from this side back, that chloride gets its hydrogen back. It is accepting one, or that means that it is itself acting as a base. This ability to go back and forth, or this taking of different forms, is what we call conjugate acids and bases. So maybe from an English class or a world language class, you'd think about conjugating verbs. That's taking one thing and putting into its different forms. Here we are kind of conjugating our molecules, turning it from its acid form with its hydrogen to its conjugate base form without its hydrogen. The base turns into the conjugate acid. As we're looking at this going backwards, our acid is donating and our base is accepting. A very common question and important thing to know is to think about these as pairs, or to think about them as different conjugations of the same molecule. So HCl and Cl minus, for example, are an acid-base conjugate pair. NH3 and NH4 are a pair, but these two things, these are my acid and base, but they're not a pair of one another. They're not two different forms of the same molecule. These are both acids and bases, but they are not paired up. So when you're asked to either label or choose some in a multiple choice question, be really careful that you are choosing the pair and not just the acid and base from one side or the other side.